So first derivatives are what we care about this week. Next week, we'll really worry about the bends, which is concave up and concave down. Okay? So it's first derivatives. If I find where it equals 0, these are the critical points. These are so important to us, okay? Because if the first derivative is 0, you could have a max, okay? Now, get used to the boxes here. This would be, remember, this is the x, the y prime, okay? A max would be if I went up, 0, down. Because look, up, flat, down. That's a max. A min, in the bottom row again of your boxes that we're going to be building all day long. A min is you go down, flat, up. That's a minimum. Now, it does not guarantee you that if you equal 0, it does not guarantee you that you have a max or a min. You have a potential max or min, because there's another style that we haven't spent too much time with, a saddle. Look at both cases of a saddle here, okay? Both places, it is definitely flat in this region, in that region. It is flat. But look at this top saddle. I went up, flat, up. And this bottom one, I went down, flat, down. Inside that, if I drew a little box right here and I asked you, hey, is this a max or a min? It's neither. Because if you try and say it's a max, I'd go no, because right there on the right side, it looks a little bit higher. And if you try and say that's a minimum, I'd go no, over here it looks like it's bending lower. So there it is flat, but it's not a max or a min, it's in the middle. So that is a neither max or min, it's called a saddle, okay? So just if you have a derivative equaling 0, that does not guarantee a max or a min. It could be that flat zone of a saddle, okay? Let's take a look at one of those in this problem here, okay? So here's my guy, and again, it's on an interval, and I want to sketch a graph based off the first derivative. Now, I've told you before with x to the fourth, those guys normally look like w's. So they could be a w, but if it's a really basic one, it is a really boring w with a really flat bottom. Or it can have where one of the bumps of the w goes lower. Or you could have one that goes like that, where you kind of lose one of the bumps. It's all part of the W form where you're kind of stretching or pulling up or down part of the those mins and max. Okay, so I don't know if it's the classic W, the really boring U, the W that's a little bit off center, or if you kind of see the flat zone. Okay, so we're going to try and figure it out. I'm going to graph by looking at the first derivative, 12x cubed minus 12x squared, and I want it equal to 0 because I'm trying to find my critical points. So I set it equal to 0. I am now going to factor out a 12x squared. I have an x minus 1 left. So it's telling me x equals 0 and x equals 1. Okay? These are my places where I could have a max or a min or a saddle. And that's the parts we want to look for. Okay, a max, a min, or a saddle. Now notice, there's only 2 of those places. So could the W work? How many places there have max, mins, or saddle? 3. So it can't be him. Could it be the boring U? How many flat zones are there? 1. So it can't be that. How many flat zones on the off-centered W? 3. Can't be that. But here, how many flat zones are there? 2. 1 here and 1 here. So that's going to be the shape of my graph, but I want to make sure I do it even better by exploring it even more. Now, question is, how many columns will I have for my kind of box that I'm going to set up for organizing? if I have two critical points, this guy and this guy, but what else do you have to put in? Your endpoints. So here's my box. Okay? And I'm going to have x equals 0, x equals 1. Those are my critical points. And -1 and 2 are my endpoints. Okay? Critical points and endpoints. Okay? Now, to get the y values. Okay? The y values are from the f of x, which comes back up to there. So, I'm going to plug in to 3x to the 4th minus 4x to the 3rd, and I need to plug in all of these values. So if I plug in -1, I get y equals 7. If you plug in 0, that's easy. You get 0. If you plug in 1, again, to the main function, you get -1. And if you plug in 2 to the main function, you get y equals 16. Okay? If you wanted to, you could already set up some of the plots here. I got 0, 0, 1, -1, 2, way up top at 16, and -1, kind of in the middle here, at 7. Okay. So I got the dots, so now we're going to look at more detail to it. I know here my first derivative is 0, and my first derivative here is 0, because we found that. Remember, we set equal to 0 and solve, and that happened at those 2 points. So those are flat zones. And since these are endpoints, you cannot tell me a slope, so you say undefined. Undefined. Okay. Now, if I want to do the sign testing, okay, sign testing on the first derivative, I would do it right here, okay, and I'm going to sign test, sign test, sign test. Okay, so a couple ways to do it. Okay, plug in maybe like a -1/2. So I'm thinking of x equals -1/2. -1/2 squared, positive. -1/2 minus 1, negative. Positive times negative, negative. Here I might think of x equals +1/2. Positive squared is positive. Positive half minus 1 is negative. That. Now here I might play with 1.5. 1.5 squared, positive. 1.5 minus 1, positive. That gets me positive. Okay? So, hopefully, you can already see from without graphing it. When I go from, I'm going to kind of focus because I can't point on the video. I'm going to point with this thing here. If I go from negative to 0 to negative, think back to our other page, the one I just did before. Going down, flat, going down. What does that make me? Is it a max, min, or a saddle? Look back on your notes from the last page. Negative, 0, negative. That's going to get me a saddle right here. Now let's look at this zone here. Down, flat, up. Down, flat, up. That means this guy's has to be a minimum. So you now know that this guy's going to be a minimum, and this guy's going to be a saddle. Let's graph it. Okay, so I have to go down, flat, down, flat, up. Okay, and we have right here this dot. This is a local and global min, And this guy here, because it went down and then down, is a saddle. So it's not a max and it's not a min. Okay. Now notice when I drew that, it was a natural tendency for me to bend it. Let me show again. I bent it up there. So that's concave up. And right here, all of that was a concave up. But right here, in between, there's just a small zone where I bent it concave down. And that's just a natural tendency of your arm. You just bend it as a natural flow, and that's typically correct. I'm going to show you that perfectly next week. With the important point, right where the purple met the green, right there, and right there, we've already told you what these are. Whenever you turn concavity, those become inflection points. And again, this is all previewing next week, but you might as well do it now just so you have it. Okay? You guys okay with that? Okay? Again, ultimate goal, become a human graphing calculator. Let's take a look at another idea. Okay, I told you critical points for the first derivative are when the derivative equals 0, and I'm adding an extra part to it, or when it's undefined. The reason is, for critical points, you're trying to find maxes, or mins, or saddles. Well, we've already talked about flat maxes, mins, or saddles, okay? But realize, if you're undefined, you can still have a max, min, or saddle, okay? So let me just kind of redraw it. With undefined guys, okay, you could easily have a max or a min. Now the saddle part you can't really have because well, I guess you could. It would maybe look like this. Let me see if I can do this. Down, down. There we go. Top guy's a max, middle guy's a min, bottom guy is, I wouldn't really call it a saddle, but I would at least call it a not max or min, okay? So, when we're finding derivatives now, we don't want to just find first derivative equals 0, we also want to find when it's undefined. Now the reason I haven't said the undefined yet is, when you go backwards and look at the ones that I've given you, x squared minus 4x plus 5, that's just a parabola, there's no issues with it. And then this one here, with the x to the fourth, no issues with it. So I didn't say anything about undefined yet because I knew I didn't give you one that would be undefined. But if I give you one like this, now you're going to see something that's going to be undefined here in a moment. Okay? This is the first time where you have no idea what this graph looks like. It's not a parabola. It's not a cubic. It's not a W. It's something to the 2/3, and you've never seen that before. Well, today, I'm going to be able to graph it pretty well with you without having to use a calculator. Okay? So first thing, we're going to take the derivative. 2 minus, let's see, that 2/3 falls, so it cancels with the 3. So minus 2x to the negative 1/3, which is f prime of x is 2 minus 2x to the 1/3, and we want to set it equal to 0. When we set it equal to 0, we are trying to find the horizontal tangent. But before you solve that, right away, this is screaming at you that this is undefined when x equals 0. If you plug in 0 right now in this derivative, you have a 2 minus 2 divided by 0. That's undefined. So that makes the whole derivative undefined. So I know this is a critical point because it could be something like that or like that. I might find a max or a min at that place. Even though I can't take the derivative, it doesn't mean that there might not be a min or a max at those points. Okay? That's the undefined part. We still need to find if this ever equals 0. Okay? So let me see if I can solve this for 0. I would move the fraction over. I would multiply up to get rid of the fraction. X to the 1/3 equals 1. So the opposite of doing, you can kind of think of it as like a cube root of x if you want it equals 1. To get rid of the 1/3 or to get rid of the cube root, you would cube it. And x equals 1. Okay? This is a horizontal tangent, and x equals 0 is an undefined. So it's like a bird or a volcano sort of thing. So 2 critical points, x is 1, x is 0, and 2 endpoints make me set up this box to help us graph things. And I forgot to erase, but I already plugged in -1, and I got that to be -5 for my y. I plugged in 0, and I got 0. Now I'm going to plug in 1, and I get -1 here. And I also want to plug in 8. That gets me a 4. Okay? Remember, those I plugged into my original black equation, which I just wrote down here so it was easier for me to see. Now, I want to get my first derivative, and endpoints are always undefined. Let's see, at 1, we found the horizontal tangent, so that's when the derivative was 0, and at 0 is when we found the undefined. Okay. Now, if you want, let's plot it out first by saying, let's see, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 8, 4, 1, -1, 0, 0, and -1, 1, 2, 3, 4, 5. 5. Now, your sign testing, when you do your sign testing for this, and this, when you look at it, you're going to have to sign test right with this guy and figure out what the values are, if they are positive or negative. Okay? A nice trick to this, though, is as long as you plotted your y values correctly, can you already tell me what the signs are between the black points? Like between the first 2 black points, I'm definitely going up. The next 2 black points, I'm going down. And the last 2 black points, I'm going back up. Save yourself some time. Again, as long as you plotted the points correctly and have the correct y values, you should know you went up, down, up. Okay? But here's the key part. It's not smooth like your hand would want it to be. Here's what my hand would want me to draw. Flat, flat, up. That's what my hand would want me to do, showing this is flat, showing that's flat, and that makes sense to me. Okay? It's not that one. Because the first guy is undefined, the second guy is flat. So I have that part right, that's flat, because I have that shown where that's flat. But this guy is not flat. Remember, since it's undefined, it's either a volcano or a bird. So in this way, it has to be a volcano. Now I can connect it, and it's going to look like this. I'll draw it in green. Okay? So I had that volcano part, and then the flat part. Okay? You did not know that. You've never seen an x to the 2/3, and you can graph it on your own to verify that that's exactly what it is. But you didn't know that until you figured out doing this first derivative test. Here, I'd call that a local min. This is the local and global max. This is a local max, even though the derivative's undefined. And this is your local and global minimum. Okay? So hopefully that's a good problem where you can see where you've never seen an x to the 2/3, but you now knew how to graph it by doing what I call the first derivative test, which is taking the derivative, taking the derivative, setting equal to 0, and creating this box. Okay? I got a couple more on the next videos.